last time I embarked on proving the following result. Then we had the following G tensor C over R, same as SL2, which is the same as all elements of all matrices of 2 cross 2 matrices of trace 0 is the algebra. This as a basis. These 3 elements F, H and E, they satisfy the bracket relations H E equal to twice E, H F equals minus 2F and E F equals H. And if rho is a, we know that all the, so there is a budgetary correspondence between of representations of SU2 and SL2C. So there is a correspondence of every representation SU2 gives rise to a representation SL2C over C, representation of SU2 over complex numbers and those of SL2C. Every representation of SU2 gives rise to a representation of SL2C and conversely. Now, and what I was attempting to do is to describe all possible irreducible representations of SU2. We know that representations of SU2 which is same as representation of SL2C, same as those of SL2C are completely reducible. So to understand all representations is enough to understand irreducible representation. Every representation is a direct sum of irreducible representations. So we need to understand irreducible representations. And it is towards that end I started attempted a proof which didn't work. So I will now give a proof which does work. It requires a little more work than what I attempted to last time. So let P be an irreducible representation of SU2. Then what happens is this: look at the diagonals in SU2 is isomorphic to the circle group S1 and it's an abelian compact group. Therefore, the entire vector space, let me write, let rho be on a complex vector space V rho. Whenever I write a representation rho, the vector space on which the rho G operates is denoted V subscript rho. is the representation space of rho. Okay. Now, so the entire vector space breaks up into eigenspaces for rho, eigenspaces of rho of T. T is the maximal torus in SU2. V rho breaks up into eigenspaces for rho T. So, and what happens is, and observe that rho H, rho of the Lie algebra of the torus, rho dot, I will call it the induced representation on the Lie algebra, is denoted rho dot, as also its extension to SL2C, induced by rho on induced by rho of G or SL2C denoted rho dot is denoted rho dot, then rho dot T will be so eigenvalues of rho T are of modulus 1, because T is rho T acts on the vector space, it preserves the inner product, and therefore its eigenvalues have to be all of modulus 1. It leaves invariant a standard inner product, some inner product, and therefore its eigenvalues are modulus. This implies rho dot of anything in the Lie algebra of T. I think I gave it I did give a notation for that. Rho dot T, Lie algebra of T, eigenvalues of product T are all in I times R right C, which implies, observe that I times H, this element H has all eigenvalues. So, rho of IH has all eigenvalues purely imaginary. Which implies, should be rho dot H has all eigenvalues real. This is true for any representation. Irreducibility is not relevant, but it is true for any representation rho. Now, all the eigenvalues of rho H are real. I now pick the highest of these eigenvalues. Let they are all real. So, and there are only finitely many. So, there is a maximum which I will call lambda, and let E0 V rho be such that rho h of E0 equals lambda. Fix a vector E0 like this. Let En Er equal to rho dot of f power r. Observe that rho h is not equal to lambda. Now consider now, then I claim rho dot E, or maybe I'll call it V naught. Then I claim that rho dot E V naught is 0, because rho dot E V naught, this is an eigenvector of rho dot h, sorry, that's right, rho dot E V naught. It's an eigenvector for rho dot h with eigenvalue lambda plus 2. Notice that rho h, rho E V naught rho h, rho E V naught is nothing but rho E, rho h V naught plus rho h, sorry, rho dot h, rho dot E, the bracket of this on V naught. And this, you know, this is rho E, rho dot h V naught is rho dot E lambda V naught plus rho dot h, rho dot E is twice rho dot E, so this is also twice rho dot E V naught. So rho h, rho E V naught, it turns out, is equal to rho dot everywhere lambda plus 2 of rho dot E V naught, which means rho dot E V naught is the eigenvector with lambda 2 plus 2 as the eigenvalue, but lambda is the maximal possible eigenvalue. So this has to be, implies rho dot E V naught is 0. Now what I am going to do is to, the next claim is rho dot f power r E naught is an eigenvector again for h, rho dot h with eigenvalue lambda minus 2r. The proof is entirely analogous. You just apply, you prove it by induction. Assume that you prove it for some r, then for r plus 1 you apply one more rho dot f. So rho dot f power r E naught. On this you want to apply rho dot h, and rho dot h, rho dot, this is, no, this you write as rho dot h, rho dot f, rho dot h minus the bracket of rho dot h and rho dot f, which gives you minus twice rho dot f on this on E naught. So rho dot f E naught, have I got it right? Rho dot h, sorry, the bracket of rho dot, yeah, and rho dot f, rho h E naught, right, that's correct. So, this gives you, oh I forgot a rho f power r, rho at f power r E naught. So, this gives you clearly rho h by induction hypothesis, rho h of rho dot f power r is lambda minus 2 r, and then applying rho dot f on that. So, you get lambda minus 2 r on rho dot f power r plus 1 E naught. The second term gives you another minus 2 rho dot f power r plus 1 E naught. So, that gives you lambda minus twice r plus 1. So, the claim is proved inductively. Proved it for r and comes out for r plus 1. So, the next point is that, yet another claim if you like, is that rho dot f power r E naught one less than or equal to, so r equals 0 less than or equal to q less than L are linearly independent if they are non-zero, if rho dot f power L is not 0. If rho dot f power L is not 0, all the intermediate things are also not non-zero, this q. Intermediate things are also, and their eigenvectors correspond to different eigenvalues, so they have to be linearly independent. This follows. Observe that rho dot f power q E naught is an eigenvector for rho dot h, and with eigenvalue so lambda minus 2q So, for this is true for 0 less than q less than L, and they are all non-zero vectors. I am saying they are eigenvectors, therefore they are non-zero, and therefore they are linearly independent. So, let n be the let n plus 1 be the smallest integer such that rho dot h power rho dot e rho dot f power n plus 1 E naught is 0, and let W be the linear span of rho dot f power q E naught 0 less than or equal to q less than or equal to n. This is all distinct and non-zero because n plus 1 is the smallest integer, such that rho dot e power n plus 1, rho dot f power n plus 1 annihilates E naught. So, these are all linearly independent. I call W the span of that claim. W is stable under rho of GC. For this you have to show it is stable under rho dot f, rho dot e and rho dot h. It is clear it is stable under rho dot f and rho dot h because there are eigenvectors for rho dot h, and rho dot f with the very choice it is clear it is stable under, it is clear W is stable under rho dot F and rho dot H. So it's enough to prove it's stable under rho dot E as well. Then it will become stable under the entire Lie algebra. So to show that W is stable under rho dot E. In fact, we claim the following. In fact, one has rho dot E of EI. Let me write. I don't know if I gave it a name. Let me denote by VR. I think I've been confusing this. I should use V naught everywhere, not E naught. Should be sorry about this. It's V naught everywhere. Here also V naught. So let me set VR to be equal to rho dot F power R on V naught. Then rho dot E of VR equals is in the space spanned by VR minus 1. See, what happens is this: F keeps pushing V naught to V1 to V2, etc. We want to say that F does it in the reverse direction. It may not be taking VR to VR minus 1, but it will take VR into a multiple of VR minus 1. That is the claim I am making. Once I do that, it is clear that the space is stable under E naught as well. So E naught takes VR into some multiple of VR minus 1. So it is clear that this set is stable under. It is clear that when R is 0, rho dot E VR is 0, and R minus 1 does not make sense. So V 0 minus 1 by definition, if you like, define V minus 1 as 0. Then clearly it is true when R equals 1. R equals 0 is true. Statement is true if R equals 0. True if R equals 0. Now suppose it has been proved for some R equal to Q, we will prove it for Q plus 1. Induction is always the standard thing that works in many of these proofs. So suppose I have shown, assume rho dot of E of VR is equals some mu R VR minus 1. Then look at rho dot E of VR plus 1. This is rho dot E of rho dot F applied to VR. By definition, VR plus 1 is rho dot F VR, and this becomes rho dot F rho dot E VR plus the bracket of rho dot E rho dot F on VR. We know by induction hypothesis this is rho dot F rho dot E VR is VR minus 1 times some mu mu R of VR minus 1 by induction hypothesis, plus here it is minus 2f applied to, sorry, have I got it right, 2f rho dot t rho dot, there is something wrong, sorry, this is mu rho dot f Vr by definition is rho dot f rho dot t Vr, just yeah, so that's right, rho dot f mu r Vr minus 2f, this is bracket is 2 rho dot f on Vr, but this is clearly rho dot f Vr is Vr minus 1, no, something wrong, sorry, it's, I should have a, I should get Vr somewhere, something is wrong, I have not got it right, rho dot f rho dot t f and Vr, that is rho dot f rho dot t Vr, rho dot t Vr by definition, sorry, it's mu r Vr minus 1. So this is mu r Vr minus 1, and here you get rho dot t rho dot f Vr is minus 2 rho dot f Vr, okay. Oh, there's, I am getting something wrong. This is rho e rho f Vr is rho f rho e plus the bracket of rho dot t and rho dot f, which is twice rho dot f and
no, that is rho dot h.
Sorry?
That bracket is rho dot h.
Yeah, it's rho dot h.
H, not f.
Oh yeah, this is right, rho dot h, right, thanks. Yeah, it's rho dot h Vr, but this is rho dot h is Vr is an eigenvalue for this, so it's twice rho dot some constant Cr Vr, and here rho dot f Vr minus 1 is Vr, so you get mu r Vr. Vr is an eigenvalue for rho dot h, eigenvector for it. So you find that rho dot r plus 1 is nothing but, so it's mu r minus 2 Cr, which is mu r plus 1 if you like. So that proves that our vector space is entirely stable under the entire Lie algebra, which implies, so you find that let us look at what happens to rho dot h. The trace of this is 0 because rho dot h is the commutator. See, rho dot t, rho dot f, the bracket is rho dot h, so the trace is 0. But if you write down the trace, what is the trace? There are some, you have the eigenvalues, so you find this implies sigma 0 to n lambda minus twice r h is 0, r equals 0 to n, which means n lambda minus twice n into n plus 1, summing the arithmetic progression, this is 0, which shows that lambda equals n plus 1, an integer, and therefore proves that all the eigenvalues are necessarily integers. Once you have lambda as an integer, all the eigenvalues lambda minus some integer, so they are all integers. So what we have shown is the following, and this, once it's stable, we know that W is equal to V because we have assumed that V is irreducible. So we know, yeah.
How did you get that summation?
Trace, what are the eigenvalues of H? We have lambda minus 2r as to varies from 0, r varies from 0 to n. So add up, you are going to get this, and you are going to get 2 into 1 plus 2 plus 3 etc. up to n. That's the arithmetic progression. That lands you in n into n, sorry, 2 into n plus 1 by 2, and this 2 cancels out, so you get only n plus 1. So lambda equals n plus 1. So in other words, the irreducible representation, the vector space V rho is of dimension n plus 1, and the highest eigenvalue for H equals n. Equals n, yeah. So the conclusion is this theorem: V is an irreducible representation of SL2C of dimension n plus 1, then V rho, the representation space, admits a basis E naught, E1, etc. En, sorry, V naught, Vn, such that rho dot H of Vi is n minus 2i Vi, rho dot F Vi is Vi plus 1, and 3 rho dot E Vi equals some scalar nu I times Vi minus 1. We assume here a basis like that, here V minus 1 is taken to be 0. So if rho is a representation of SL2C of dimension n plus 1, then it admits a basis like this. So it's clear from this there is one and only one irreducible representation in every dimension n. The point is that assuming it's irreducible, you can determine nu I by an induction. I have not worked it out. You can see that nu I is determined by an induction. The first one, when you start with rho dot E of rho dot F V equals rho dot F rho dot E V minus plus rho dot of bracket E F on V, on V0. Apply this on V0, what happens? So rho dot E of rho F V0 yeah, if I look at this, I am writing it as rho F rho dot E V0, but this is 0. So I am left with rho of E F on V0, which is rho H on V0, which is, by our assumption, it is n times, by our computation it is n times V0. Start off with that, and then in every stage you can determine nu I completely by induction. Nu I are uniquely determined by induction. All this goes to show that there is one and only one irreducible representation up to equivalence in every dimension n. of dimension n up to equivalence. One consequence is this. Observe that if you take an irreducible representation, rho of f with respect to the basis E naught, E1, etc., En, rho dot of f has the form zero on the diagonal, 0 in the super diagonal, and 1 in the sub diagonal. 0 all over above the diagonal, but sorry, the sub diagonal also is 1 and rest is 0. After all, E naught goes to E1, E1 goes to E2 and so on. So that is the way it behaves. So in other words, you can see that this rho dot f is a nilpotent matrix in the Jordan canonical form. Rho dot of f is the nilpotent matrix in the Jordan canonical form. Okay. And we know, but this comes from a representation. So what happens is this: given, and more generally, suppose you take any nilpotent element, the Jordan canonical form gives you blocks of this kind. So in general, n nilpotent, maybe I call it u nilpotent element in GLNC after conjugation, we know it takes the form blocks like this, in each of which in each block it has this form. In each block the matrix is 1 1 1 below the diagonal, takes this form. Now this means I can break the vector space into direct sum of number of subspaces, in each of which the nilpotent element acts like this in the Jordan canonical form. But that means in each of them you have a representative SL2 which goes into it, with f going into this Jordan canonical form. So the conclusion is sorry, E naught, oh sorry, thanks, I am sorry, Vn. Okay, so the upshot is the following, which you can call theorem if you like. Given any nilpotent matrix in GL and C, there exists a homomorphism matrix in M and C. There exists a homomorphism from rho dot from SL2C M and C such that rho dot F equals not given a U, given any important matrix U, rho dot F equals U and rho dot H is diagonal all entries integers. So, the Jordan canonical form actually means that you can push a whole SL2 with the nilpotent the element E F in the SL2 going over to the given nilpotent matrix. So, that is the offshoot of reducing things to a Jordan canonical form. Any nilpotent can be reduced to Jordan canonical form, and so that is the now. Okay, there is some, this representation, the unique representative dimension n has also another realization. It goes like this. This was explicit by giving a basis and so on. You can also make it equally explicit by doing the following thing. Let V, now let nu denote the representation SL2C to the inclusion M2C be the natural representation. Now, actually it turns out that nu is equivalent to the dual of nu star, where nu star of a element x in SL2C is minus transpose x. For every x SL2C. Basically, what it does is to take the upper triangular matrix and lower triangular one, and vice versa. The diagonals remain unchanged. Why is this true? This is true because, in fact, the alternating bilinear form on C2 defined by let me call it A, defined by the basis, you have standard basis 1 0 and 0 1. Let me call this basis W1 W2. AF W1 W1 equal to AF W2 W2 equal to 0, whereas AF W1 W2 equals minus A of W2 W1 equal to 1. That's a non-degenerate alternating form on this, and it is easy to see that A of GW1 GW2 equals A of W1 W2 for every G in SL2C. It's an alternating form which is left invariant by the group, and therefore by its Lie algebra, but in Lie algebra, invariance under the Lie algebra means the following: equivalently for every I should write, this is the alternating polynomial, I should write a w w prime for every gene and every w w prime in C2. It's not just those two vectors, you have to do it for all vectors. In particular, a w1 a g w1 g w1 prime w2 will be 0, sorry, a g w1 g w2 will be 1, a g w1 g w1 will be 0, and so on. I mean, this condition, when you write down for w equal to w prime, are such pairs w1 w2 or w2 w1 or w1 w1 w2 w2. To do for such pairs, you get it for all pairs because of bilinearity, and it transforms into the following condition on the Lie algebra: AF x w1 w w prime plus AF w x w prime equals 0. This is entirely equivalent to that. One way of seeing it is to observe that A of x, I should call it xw, if you like, xw is nothing but d by dt t equals 0 of exponential tx w. From this formula and applying Leibniz, you find once you use this, apply, put in xtx x here and then differentiate, apply Leibniz formula, you get this kind of thing. Okay, so it turns out that the space of representation of the space of linear forms on the two-dimensional vector space is equivalent to the original representation. Now the point I want to make is the following: the representation of dimension n is the same as the irreducible representation is equivalent to the natural on the symmetric algebra Sn minus 1 the dual representation, or if you like, it is equivalent to the symmetric n minus first power of nu star. It can also be, I can also make it nu because nu and nu star are equivalent anyway. So what do I mean by this? What is symmetric power? It's equivalent, that is the same thing as, this can be thought of as space of homogeneous polynomials in two variables of degree n minus 1. N is 2, I am going to look at symmetric space of homogeneous polynomials of degree 2, degree 1. If n is 2, I am looking at homogeneous polynomial of degree 1 in two variables. That is nothing but linear forms on the two-dimensional vector space. So, polynomial of degree 1 is precisely linear polynomial. Homogeneous polynomial means linear form, that is what it amounts to. In general, you have to look at polynomials of nth degree, then you will get an n plus 1 dimensional vector space. If you take polynomials of degree n plus 1 in two variables, in degree n in two variables, the dimension is n plus 1. You start off with x power n time, then x power n minus 1 times y, x power n minus 2 times y square, and so on. So you get exactly n plus 1 of them. Okay, so another concrete realization, one way of doing it is of course what I did already by looking at the highest eigenvalue of rho h, and then that gives a description. This is an alternate description which is equally pleasant, if not pleasanter. You look at you have the group or the Lie algebra operating on a vector space of two dimensions, and therefore it operates on homogeneous polynomials on that vector space of various degrees. And for each degree you get a representation, and it turns out it is an irreducible representation. And to say that it is equivalent to this, is equivalent to the representation, the irreducible representation of dimension n is equivalent to that, I will leave it to you to work out as an exercise. It is a matter of change. See, if you look at the homogeneous polynomials x power n, x power n minus 1 times y, etc., up to y power n, that is going to be a basis for all homogeneous polynomials. Every homogeneous polynomial is a combination. And then if you apply the Lie algebra, you will see what happens. It will take x power n y, first if you apply e to x power n, it will take it to 0, as you can easily check. If you look at the group level, the torus element will take x power n, it will get multiplied by the highest, on x, if it operates by something, say multiplication by t, then on x power n it operates by multiplication by t power n. Tx power n is t power n. So the nth power. So if you look at h, the corresponding element h here, it will simply multiply. It will act by multiplication by n. That's what on x power n. Then the next one, x power n minus 1y, it will operate by n minus 2 and so on. N minus 2, n minus 4 and so on. Finally, it will end up in minus n. When you go up to n times, you keep applying f n times, you will end up with the right thing. Okay, so and then it is a matter of we gave one basis in which f becomes 1 1 1, but here this basis f will not become 1 1 1, it will become some other numbers, some binomial coefficients will be involved, as you can see. Okay. So the one way of looking at irreducible representations is to say simply they are represented symmetric powers or equivalently on the space of homogeneous polynomials on the original vector space V2. This is a complete description of the representation of it. And it is also clear what about the character of the representation. So if you look at it from the point of view of the torus, acts on n-dimensional vector space V, or let me write n plus 1 dimensional vector space with basis V naught, V1, etc., Vn, with Vi as eigenspace. This is the circle group, remember, corresponding to the eigen character T2 T power So what happens is, or if you like, e power I theta, e power I n theta. So the character of the representation is, which is nothing but t going to trace t as far as the torus is concerned, and the character is entirely determined if you know what happens to the torus, because every element is a conjugate of the torus and the trace function is conjugation invariant. So what happens is this: trace of t of rho t, rho a, let me write, it's an n plus 1 dimensional representation, so let me call it rho n plus 1 t, is going to be sigma e power I q t, q equal to, well, q equal to minus n to plus n, or I should say it's not I q t, but how should I, t operates as t power I, okay, n plus 1 t, yeah, operates as n there and goes all the way, okay, e power I q t is right, which comes out to be e power n plus 1 t minus e power minus n plus 1 t by e power t minus e power minus t. Everywhere, sorry, n plus 1 I t, I t e power minus I t. So this is the formula, otherwise it's essentially sin n plus 1 t by sin t. Those who are familiar with Fourier series will recognize this as the kernel of, which I don't know what the kernel is called. What name does the kernel go by? It's sin n t by sin t. It's not the Dirichlet kernel. Yeah. I suppose it's called the Dirichlet kernel. Anyway, so this is the, okay, so sum, trace is sum of this and this is equal to this, and what we are aiming at is a general formula in the case of semisimple, compact semisimple groups of a similar kind. That is our ultimate aim, to get a character formula, formula for the character. So, but before embarking on that, I have to do a lot of preliminary work. Firstly, you see, I said that lambda of h, if lambda is a eigenvalue of h in V rho, then lambda is an integer. In fact, if the dimension of V rho is n, it is an integer between minus n and plus n. And it jumps by 2. In fact, okay. So, if dimension V rho is n plus 1, the eigenvalues are of multiplicity 1 and rho irreducible, and constitute the set n minus 2 etc. up to minus n. Each time you jump by 2, so your range is from n to minus n. So, notice that if n is odd, sorry, if n is even, that the dimension is odd, then you will get somewhere here 0, and the eigenvalues will lie symmetrically between 0. If n is even, if n plus 1 is even, n becomes odd and you won't get 0 here, you will get from the odd number to odd. It is jumping by 2, so there is no middle number. So, if you the eigenvalues of H are all odd or all of them are even. Eigenvalues in irreducible representation of H are all odd or all even. Well, H is of some fixed element. If I look at the Lie algebra T and denote by H I T, it is a one dimensional thing, and if I take any H prime in H prime is of the form some alpha times H, or maybe let me write QH, where Q is in R. Then the eigenvalues of H prime are all of the form R Q times R minus n less than or equal to R less than or equal to n. Q times, have I got it right? Sorry, goes from minus n to plus n, jumping by 2. So, I should say minus n plus 2q 2I less than or q less than or equal to, sorry, let me write n minus 2q times, sorry, n minus 2 times 2 R times q minus n less than or equal to R less than or equal to R integral. Okay, so the eigenvalues are of this form. The reason I am doing it like this is the following. This means you find that the eigenvalues of H prime are multiples of by n minus 2 R of q, and q itself is the eigenvalue q itself is the eigenvalue of H prime in G itself. H acts by 2, so 2q is the eigenvalue. 2q is the eigenvalue of H prime in G. Why am I saying putting things in this way? So, if I look at the eigenspace for H with eigenvalue lambda, then we know that lambda H by see the eigenspace for the entire Lie algebra, let me write, of H with eigenlinear form. Lambda, if you have an eigenspace eigenlinear form lambda, then you have lambda of what I have written here is lambda of h by not sure I am putting it, let me write alpha of h. Alpha is the eigenvalue, sorry, eigen linear form in G. G itself is a 3-dimensional representation, and I call that corresponding eigenvalue, eigenlinear form I call alpha h. Then what you find is that lambda h by alpha h is what is it going to look like? Lambda h is n minus 2rq divided by, when I take h, I am going to get n minus 2rq by 2 here. So, it is a half integer, this number. So, lambda h by alpha h is a half integer, and I can replace h by any h prime. So, what you find is lambda h twice this is in Z always. For any eigenlinear form in a representation, you find that 2 lambda h by alpha h is going to be an integer. I am going to, this is an important fact which we will use repeatedly later. Okay, at this point I now go over to general sum-simple Lie algebra and analyze its structure a little bit. Yes?
Can you repeat the argument from?
See, the fact that you can, see h prime is after all qh, and if I look at lambda of qh, q pulls out. Okay, lambda h prime by 2 alpha h prime, you can write it as q times lambda h divided by q times alpha h prime, alpha h, and then the q cancels out, we find lambda h by alpha h is we know it's a half integer. So, instead of h I can replace it by any multiple h prime. If I this I know is a half integer. If I replace this h by multiple, say q times h, then both the numerator and denominator get multiplied by q. So, it cancels out. So, the number whatever h, instead of h I can put h prime and still can claim it is a half integer, that is all I am saying. So, this ratio is a half integer for any h in h. You will see it is a remark which is going, you will see its significance a little later. Okay, now let me get back to general compact sum-simple group. We have seen G compact semi-simple, and let me denote by T maximal torus, compact connected always, T a maximal torus, and the corresponding Lie algebras of G, and this T in G Lie subalgebra corresponding to T. Now, look at GC, which is by definition G tensor C over R. This decomposes into T tensor C plus sigma G alpha, alpha and delta, where these are complex vector spaces. So, GC G alpha delta is set of a finite set of characters on T, and G alpha C, a set of elements T, sorry, V in G add dV equals alpha T in V for alpha and delta. Finite set of characters, finite set of non-trivial characters. So T tensor C corresponds to the eigenspace which corresponds to the trivial character, whereas this rest of them correspond to non-trivial characters. We have already seen G alpha are of dimension 1 for every alpha in delta, and G beta, and G, if alpha in delta minus alpha is also in delta. Now we know that we have seen that the centralizer of, let me write T alpha is the connected component, identity connected component of 1 in the centralizer of T alpha, that is, sorry, T alpha is a connected component of kernel T, kernel alpha. Alpha is a homomorphism from T, the circle, it is a non-trivial homomorphism, so it is onto, and the kernel is necessarily one dimension, torus of one dimension less, contains a torus of one dimension less, and T alpha is that torus, connected component of kernel alpha, connected component of 1 in kernel alpha. Kernel alpha is a closed subgroup of T, and all closed subgroups can be characterized. To take the connected component, it has to be a codimension 1 torus there. Anyway, so if alpha and delta minus alpha and delta, all this is true. We have seen this, and what is more, we know that I also showed it last time, that bracket ZT alpha, so see ZT alpha is actually connected, but let me take the connected component ZT alpha to be identity connected component of centralizer of T alpha. Then we have seen that ZT alpha is a compact group, it breaks up into T alpha times ZT alpha, and this group we saw was 3-dimensional. The commutator subgroup, this, let me denote this by G alpha. G alpha is compact, semi-simple, connected. G alpha again, this is once ZT alpha is, I have taken ZT alpha to be a connected group, so the commutator subgroup is necessarily connected. So G alpha is connected, G alpha is connected compact semi-simple group of rank 1. So we know that G alpha is isomorphic to SU2 or SO3. Now let us look at the adjoint representation. of the big group G in its Lie algebra. We know that it breaks up into sigma G alpha like this, and choose an element E alpha in G alpha for all alpha in some delta prime such that it contains one and only one of the roots plus minus beta. So the elements of delta are called roots. With respect to T. So we know this group G alpha is either SU2 or SO3, and in any case SU2 is the covering of G alpha. It could be G alpha itself, but or a two-sheeted covering. So we choose fix for each alpha, fix one, that is delta prime contains exactly one of alpha and beta and minus beta for every root beta. Fix a non-zero element E alpha in G alpha for alpha and delta prime, and for now the killing form we know is non-degenerate on the entire group, on the entire Lie algebra G, because G is semi-simple. We have seen that. It's in fact it is negative definite. So what you can do is the following. You can therefore, and we know that the killing form Bg is such that Bg of E alpha E beta is 0 if alpha plus beta is not equal to 0. One, this is one. Bg restricted to H Bg restricted to Tc is non-degenerate. And finally, Bg restricted to Ce alpha plus Ce minus alpha is non-degenerate. Once you have this is clear because you apply on any element x E alpha, and then so suppose you apply add E alpha, add E beta on any element E gamma, it is taken into G alpha plus beta plus gamma. Apply it again, it goes to G twice alpha plus beta plus gamma and so on. And therefore, it's a nilpotent endomorphism for that reason, and therefore its trace is 0, which shows that this is, if alpha plus beta, this will work only if alpha plus beta is not 0. So if that happens, then you know it's nilpotent, so this first condition is satisfied. Secondly, so I know all the entire Lie algebra breaks up into T plus the orthogonal complement. It's easy to see that T is orthogonal to all the G alphas, and therefore it has to be, when you restrict Bg to that, has to be non-degenerate.
Can you recall what is Bg? I forgot what is Bg.
The killing form.
The killing form for Bg you said?
B sub G is the killing form
No, the killing for.
on G.
Oh, killing form. Oh, sorry.
All right. So, these are easy things to check because of the fact that T alpha and E beta is orthogonal. Of course, I also should say it's also Bg V alpha H Tc, complex equation of C is 0 for every alpha. So, once you have this, it is clear that once you have these two things, it is clear that Bg restrict to E alpha C E minus alpha must be non-degenerate because both these are orthogonal to all the other Bg E alpha, and here they are orthogonal to all the other E betas, and it is also orthogonal to Tc. So, this must be non-degenerate, and once again this is orthogonal to all the G alphas and for every alpha, and therefore Bg restricted to Tc has to be non-degenerate. We actually know that Bg of HH is greater than or equal to 0 if H is in I times T. I will call I times T, I will call H. So, our killing form is actually positive definite on H. It is negative definite on T and therefore positive definite on H. Okay. So, now the next thing I want to say is the following. Let us look at you have G, you have the group G alpha, which is a 3-dimensional group isomorphic to SU2 or SU3. Now, look at the adjoint representation of the group G in its Lie algebra. It goes into GL of GC. You have look at this adjoint representation and restrict this. Let us call this at G. Restrict at G to G alpha. You can, G alpha is either SU2 or SU3, but any representation of G alpha can be regarded as a representation of SU2 because SU2 is a 2-sheeted covering. So, there is always a mapping from SU2 to G alpha. It is either isomorphism or a covering map. In any case, any representation of G alpha can be regarded as a representation of SU2, and we know how representatives of SU2 behave. And what about the Lie algebra of G alpha? I should okay, Lie algebra, maybe I will call this not G, let me put up alpha here. Notice that G alpha is same as G minus alpha, the two are equal. So, let me call this G minus alpha is central to ZT alpha. T alpha, the group T alpha is the same as the group T minus alpha. The kernel of alpha and kernel of minus alpha are the same. Minus alpha means alpha inverse. So, the kernels are the same. So, you find that you have this and now we look at, let me also denote by G alpha the Lie subalgebra corresponding to G alpha, and you have the complex equation which I write to G alpha C which is G alpha tensor C. Now, the Lie algebra G alpha C is going to be like this. When you take commutators, you find that G alpha C, I mean G alpha C is after all the Lie algebra, the commutator of what I call centralizer of T alpha, ZT alpha. Now ZT alpha has a consists of T, the total part, ZT alpha, the total part plus E alpha and E minus alpha. Those will be the entire, that will span the entire group ZT alpha. And what about the commutator group? If you take anything in the torus and take a bracket of E alpha, it falls into a multiple of E alpha. Similar thing is true of E minus alpha. And you take a bracket of E alpha and E minus alpha, that's the only extra element you are going to get, because every other commutator is either E alpha, E minus alpha kind of thing happens. So you find that this is nothing but G alpha C is the commutator subgroup, is the commutator algebra, which is C E alpha, C E minus alpha, C E alpha plus E minus alpha. Let me denote by E alpha, E minus alpha, the bracket by H alpha. So you find that this G alpha C has a base as E alpha, E minus alpha, H alpha, E alpha as a basis. And you also have, we have assumed that E alpha, E minus alpha, this inner product with respect to G is 1. That is how we chose E alpha and E minus alpha. Now, sorry? H alpha is by definition this. E minus alpha, H alpha, E alpha is the basis of G alpha. H alpha is the is the basis of G alpha C. Sorry?
H alpha definition.
H alpha definition is here.
Bracket same. E alpha, E alpha.
E alpha, E minus alpha, sorry. E minus alpha it should be. E alpha is 0, so it won't. The E alpha, E minus alpha are chosen like this. Now, I want to see what happens to H alpha scalar product with H beta, alpha beta roots. This inner product of this is equal to H alpha inner product of E beta, E minus beta, and that is equal to because of the invariance of the Killing form, this is equal to, I am writing the Killing, I am Bg is written as the definition of Bg, I mean this the definition of this product. So H alpha E beta E minus beta, which can be, because of the invariance you find that this is the same thing as H alpha E minus beta E beta. The invariance under E minus beta gives you this. So this is the invariance of the Killing form. Okay, but what is this? This is nothing but minus H alpha E minus beta is minus beta of H alpha, so you are going to get beta H alpha E minus beta E beta, which is same thing as beta of H alpha, because we have chosen E beta E minus beta so that this inner product is 1, beta H alpha. So where?
Above that, where you are choosing.
Huh?
Yeah. No, the line above you are choosing E alpha,
E alpha E minus alpha is 1. I wrote it E alpha earlier, it is wrong. E alpha E minus alpha is 1. E alpha is inner product is 0 because add E alpha square is nilpotent.
True. But should be E beta or? Because
I am calculating H alpha inner product with H beta. That is same by definition H beta is E beta E minus beta for any beta. So look at H alpha, the inner product is same as H alpha, inner product with E beta E minus beta, and the fact that it is invariant as killing form, I am applying E minus beta on this, which is same thing as shifting it to this side, E minus beta on the right, but with a negative sign. So I will get minus H alpha E minus beta E beta. But H alpha E minus beta by definition is beta of H. Beta is a root space for the entire, is an eigenspace for the entire Lie algebra H. So it becomes beta of H alpha times E minus, sorry, this is what you are saying, right? Thanks. E minus beta E beta, which is 1 because the killing form is symmetric. E beta E minus beta is same as E minus beta E beta. So that gives you beta H alpha. So what you find is that H alpha are such that the inner product of H alpha with H beta is the same thing as evaluating the linear form beta on alpha, or you can reverse the roles of alpha and beta. It is also same as alpha H beta. Yeah, you could have, instead of writing alpha here, put beta here and alpha minus alpha here. Then you find you will end up in saying alpha of H beta. So this same as in other words, you see a non-degenerate bilinear form gives a mapping of the space into its dual. Okay, and what we have done here is to essentially alpha going to H alpha is that map. Alpha is a linear form, it defines an element on the linear forms on that, so we get so that is what is happening. So, well, I think I should stop here. I am already overstepped my time, but anyway, these are things which I will use freely next time. So come prepared with this as known. I will say something about it, but essentially I won't repeat all the arguments to prove things about this. So you have this, and we'll also.
H alpha is canonical. Somehow it depends only on alpha and not on.
No, it depends on the Lie algebra because the killing form is important here.
No, it doesn't depend on the choice of E alpha. Somehow E alpha is arbitrary at the moment.
Yeah, right. But the point is that E alpha is arbitrary, but the point is that if you multiply E alpha by, you can only do it, it is one dimensional, you can only multiply by lambda if you want to choose a different lambda, and then the E minus alpha gets adjusted but getting multiplied by minus lambda inverse. So because of that, E alpha E minus alpha will be the same, whatever E alpha you choose, you will get the same H alpha. H alpha is independent of the choice of the E alpha. Once you choose E alpha, E minus alpha gets chosen. E alpha in delta prime is what I choose, and then E minus alpha gets chosen. If you modify the definition of E alpha by multiplication by multiplying it by lambda, E minus alpha gets multiplied by lambda inverse because you want the inner product to be 1. So that takes care of it. So, and let me also introduce one other notation. The bracket E alpha E beta, we know this falls into if alpha beta are in delta and alpha plus beta is not 0, then this is equal to n alpha beta E alpha plus beta, provided E alpha plus beta is a root. If E alpha plus beta is not a root, then n alpha beta has to be 0. N alpha beta equals 0 if alpha plus beta is not in delta. So here are we have a complete set of the constants for the Lie algebra. All the bracket operations are known once you know the n alpha beta for a different alpha beta, and we know that the H alphas commute, and we know what H alpha does to E beta. All the commutation rules are given. So from now on, this Lie algebra G will have a basis consisted of E alpha E minus alpha with E alpha E minus alpha equal to 1, and some out of the H alphas are not necessarily linearly independent. They will contain a linearly independent subset which we will use as a basis for the real algebra. I will come to that next time. What subset of H alpha you choose, we will see. Okay, at this point I will stop.